So in our original orientation, we have a 12 KSI compressive stress on our X faces, 8 KSI compressive on the Y faces, and 4 KSI of shear stress. So we need to find all of these values. We'll start by identifying in our original stress state what our normal stresses are. They're compressive on X and on Y. So on X, we'll have a negative 12 KSI. And on Y, we'll have a negative 8 KSI. And our shear stress state on our positive face, it's pointing in the positive direction. So we're in a state of positive shear stress. So tau xy is a positive 4 KSI. So we can use this information, again, to find principal stresses, max shear stress. We'll need to know the average stress so that we can draw this picture. So like I did the other day, if we start by finding the average stress and the max shear stress, that makes finding the principal stresses easier because we kind of have half, each one is half of the problem of finding the principal stresses. And we need the average stress anyway. So again, average stress is just, as the name implies, the average of our two normal stresses in our original case. So I have negative 12 plus negative 8. Which makes our average stress negative 10. And the maximum shear stress, using the equations we had before, it's sigma x minus sigma y over 2 squared. So that'll be negative 12 plus 8 over 2 quantity squared plus tau xy squared. So for tau max to 3 sig figs, 4.47 KSI. So these both things we'll need for our actually second calculation, finding the, when we go into our maximum shear plane. But I'm actually going to go back to the principal stresses. Now that I have this information, I can easily find my principal stresses, sigma 1, sigma 2, is just sigma average plus or minus tau max. Or as you have on the formula sheets, it's just written out exactly what we did in these steps. But it's the same thing. Right, so I need negative 10 plus or minus 4.47 KSI. So my principal stress 1 is going to be sigma average plus tau max, which is going to be a negative 5.5. Sigma average minus tau max, negative 14.5. Again, by the convention of how we report this or how we notate this, sigma 1, the rule is sigma 1 is always more positive than sigma 2. And then my principal plane, I can find by using 1/2 times the arctangent. Negative 12 minus negative 8 is a negative 4. So we have 8 over negative 4, and the signs here are important. Our sigma p is a negative 31.7 degrees. And that repeats every 90. We have our principal angle. We have our principal stresses. Now we can draw our stress state when we're in the principal stress state. So we're going to take our original element that we were presented and we're going to rotate it clockwise 31.7 degrees. So it's originally xy this way. So x is going to tip down and y will tip to the right, 31.7 degrees. So x prime is now facing down and to the right. But I still have to check, does the x prime face have sigma 1 or does the x prime face have sigma 2? And for that, I have to do my stress rotation to calculate sigma x prime. So as we saw before, sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine negative 63.4, 2 times this angle that we're rotating here, plus tau xy sine negative 63.4. And we should get here negative 14.5 KSI. If we put in our original values here, rotate into the principal stress position, our x prime face has sigma 2 acting on it, the compressive 14.5 KSI. Which means we don't have to do the rotation for y prime because it will have the sigma 1 acting on it, negative 5.5. Right. Again, in our principal rotation, shear stress is always 0. So we only have sigma 1 and sigma 2, those normal stresses acting on it. This is our complete, then, stress element rotate into the principal plane where we have sigma 1 and sigma 2. Right. Questions on the first part, finding the principal stresses and drawing it in the principal plane. The second part, I'm interested in looking at the maximum in-plane shear stress, which I've already actually calculated its magnitude, and I've calculated my average stress. All I need to do now is, in order to draw it, I need to know how much do I have to rotate it to get into the maximum shear stress plane, and in what direction will the shear stress be acting is my other concern. So to find the angle to get into my max shear stress plane, going to my other formula here, it'll be negative sigma x minus sigma y, which is going to be, again, negative 12 plus 8 is negative 4. Over twice tau xy is positive 8. Okay, so those both become positive. I take the arctangent, and for this one, this is where I get a positive 13.3 degrees. Again, it repeats every 90 degrees would also take me into that shear stress plane. So I am tipping now counterclockwise 13.3 degrees to get into this plane. And when I'm in the shear stress plane, every face has the same normal stress on it. In this case, it's the average stress, negative 10. So a compressive stress on both my x prime and y prime face. And I know the magnitude of the shear stress is going to be 4.47. But again, I don't know its direction. I don't know is it a positive shear stress state or a negative shear stress state. So that's where I have to now do a rotation of the 13.3 degrees to see, is this going to be a positive value or a negative value? So I need to use the sigma x minus sigma y over 2 times now the sine, and this is negative, of 26.6 degrees plus tau xy cosine 26.6. So if I plug in those original values, I put it through this positive rotation of 13.3 degrees, I get a positive value of 4.47. So it has to match magnitude-wise what I get over here, but this will always be positive. Again, this will be positive or it could be negative, which will tell me the correct sign. So I know that I'm in a positive shear stress state when I'm in my shear stress plane. So if I'm in a positive shear stress state, on my new positive x prime face, I'm going in the positive y prime direction. Again, my value, 4.47 KSI.